Next up, we have Kari Pulli from NVIDIA.
So I'm going to talk about how to do 3D programming and camera programming on Android devices. So the topics I'll cover is OpenGL ES 1.0, X 2.0, WebGL, OpenCV, and FGAN. So the first three are already existing Khronos APIs. OpenCV or subset of OpenCV is a potential candidate of future API, and FGAN also might influence some other camera-based APIs in Khronos. Hopefully will. So probably have already heard what OpenGL is. Anyway, so starting from 3D vertices in some coordinate system, you project them onto camera. And then you connect them to triangles, you get solid surfaces. Then if you add light sources and if you have surface orientation information, you can shade the output image. To add more realism, you can add texture mapping, you can render shadows. And that's then you get nice pictures. And then OpenGL ES were starting from trying to take this OpenGL to mobile phones, but it was considered to be too big, and it really was too big, especially at the time about 10 years ago. And the idea was that let's take OpenGL and let's subset it for a more compact API that could still run on cell phones. And here are some pictures from my team at the time when I was at Nokia. We had first we had this Nokia GL before OpenGL ES even existed, and we shipped that on a cell phone in 2002. The display was really nice. It has like 1 bit per pixel depth. So we rendered into a single channel, a single intensity channel of 8 bits, and then we ethered the output. And the screen size was 65 pixels this way and 96 pixels that way. So we've come a long way since those days. So the starting point was OpenGL 1.3. There had been lots of kind of redundancy that had come into the API, and we just mostly wanted to get rid of the redundancy. So one of that was the GLBD and GLN concept, and that was replaced by this vertex arrays concept, which executes faster, and then there's only one way to kind of define the data. The API becomes more uniform and compact. Okay. And this was we started shipping in 2004. The first implementations were software implementations. Then, but the standardization continued right away. In the ES 1.1 we added more features that are kind of hardware oriented, such as bump mapping, which allows you to add detail without having to add much geometry. And another feature that was added was skinning, that allows you smooth animation, so like human-like objects. And this shipped already in the following year, 2005, and this really started the era of hardware accelerated 3D graphics on mobile devices. Now about Android. Android SDK is based on Java. All of the Khronos APIs are C-based, so something needs to be done there if it's used there. But so Android's Java is very similar to Sun's Java, but different. The UI libraries are different. There's a different virtual machine, but otherwise the language itself is the same. There's this developer at android.com. It's a one-stop shop for Android tools and documentation, but really when you want to get started with Android programming, I would recommend you to go to the NVIDIA website and get this package, which install all of the tools in one go. if you go to the Android website, it tells you, well, go to the Oracle website to get the Java SDK, and then, okay, now you get the SDK, and then if you want the native SDK for C to C++, that's over there. And by the way, you need Eclipse, and that's over there, and then there's like half a dozen other tools. So this one is way easier. Android is quite fast developing OS, and you can see many different versions of Android that have added various new capabilities. This from last summer, kind of distribution of different versions on the market. So this is just from the statistics from the Android marketplace. This distribution of devices access the marketplace. Just 1 month later, you can see that the Gingerbread, which was then, well, the Honeycomb was the newest then, and that had increased by 50% in 1 month. Gingerbread percentage increased by 100% in 1 month. So, and also if you look at Android in general, it's now, the growth has been really fast. It's now over half of all the smartphones. So if you look, put iPhones, Blackberries, Symbian devices, Windows phones, Bada, all of those together, they're smaller than Android in terms of numbers of devices. There's a very nice OpenGL ES tutorial available on the Android pages. I'll run through that. This is a Java-based example, so they have created Java bindings to OpenGL ES. So you would start Eclipse, create a new project, and select it to be an Android project. Then you give it your project a name. You select which SDK you use, and you should kind of select the oldest SDK in which your application runs that has all the APIs that you need. Because that means that then your application will run on most devices. And then you give a package name with this kind of inverse URL notation. And then that's what you get. So the system now generates you all these files. And this is the interesting file for now. That's kind of the main file. You see its name, it's called activity. So in Android Java, all these applications, or the kind of main part of the application, or the main UI, they're called activities. And you can kind of memorize it from that only one application at a time is active. And then it's paused, so activity is activated and paused and resumed and so forth. So here's the hello OpenGL is one of the activity which extends activity, and by default it just puts a blank UI element there. We modify it with this. So there's the first thing we do is we add a couple of new headers for OpenGL. Then we create this GL surface view, and we make that the main kind of UI element. And then, well, because it's our class, we need to define it, that that's here. We also define our renderer, and that's where all the action is. So we need to create another class, and we're going to put that to a different file. And this stuff is just a kind of UI behavior, a standard UI behavior. So when the UI wants to pause the application, then we want to signal that to application so that it doesn't keep rendering and wasting battery. This is the renderer file, and we have 3 methods there. There's the on-surface gradient. This is called only once, and that sets things up. In this case, we set the clear color with which the background would be will be cleared into uniform gray. And then we have this on-draw frame. This is called for each redraw element, and that's where most of the OpenGL stuff will live. The In this case, we just clear the frame and don't do anything else. And this is called whenever the surface changes. For example, if you rotate your handset from vertical to horizontal orientation, you would get different width and height. So now we can get that information and set the viewport correctly. So that, and in this case, we just render the whole screen. And here's their exciting Hello OpenGL ES application, all gray. But it's not so exciting, so we need to extend it a little bit. So let's add a triangle. And so the background clear color that we already have. Then let's define coordinates for an equilateral triangle. Let's just put them into an array. And then because we have to pass, this is Java code, it's not C code. And Java doesn't understand the pointer the way as C, so we need to package it inside of this float buffer, and then we can pass the float buffer as if we pass pointers in C. So that's the container for the data. And then let's enable the workspace and need to add a couple of imports. Here's the draw method. The GL clear call we had already. Now we have we set the color for the triangle, and it's going to be kind of greenish yellow. And then we pass this data into the vertex pointer and tell that please give us triangles starting from 0 using 3 vertices. And here's the output. And then the coordinate system, the default coordinate system goes so that the screen goes from -1 to +1 in both x and y. And if we look at this first vertex, that's going to be there, so -half, -1/4. But we wanted to make an equilateral triangle that doesn't look very equilateral. And now it looks again different if we turn it around. So because the coordinate system is fixed to the screen size, that's a problem. So let's use some matrices. The old OpenGL had this couple of special matrix types. There's the projection matrix and a model view matrix. And here we use projection matrix. So we tell the matrix mode to be projects, and then we initialize it to be identity. And then we call this utility called geofraster. It says that the screen will, also we calculate the aspect ratio of the screen. And we put the x extent to be from minus ratio to plus ratio. Then we put the y ratio to be from -1 to 1. And this is in the near plane, which is at distance 3 in front of the camera. And the back plane is at distance 7. And everything that is going to be visible has to be in this box. Then we have this other mode called model view mode. So this we do it in our drawing routine. So first clear, model view mode, set the identity matrix, and then use a utility called look at, which places, in this case, it places the camera. So we have a camera here and it points somewhere. So the location of the camera is this eye, and we place that to be 0, 0, -5. Then we want to orient the camera. We put it in target. So in this case, we point it towards the origin. And then we also specify up vector because there's one more degree of freedom for the camera. We need to figure out the rotation. And now we give an equilateral triangle. A little bit more about OpenCL transformations. So this would be, if you want to draw this kind of tilting scaled house, we would start by starting with model view, matrix, setting to identity, then translate, rotate, scale, and finally draw the house. But that's kind of weird because it looks like it's backwards. So if we have this coordinate system here, we first scale it, and then we rotate it, and then we translate, but the scale comes last. So an intuitive way to read these things is that you render last, and then you look at how it's transformed from last to first. But an alternative way to think of it is that you actually, these things, they modify the coordinate system. So with identity, we set up the coordinate system. With translation, we move the coordinate system. With rotation, we rotate it. And with scale, like these tips become bigger, we scale it. And then we draw the house in this coordinate system. This diagram shows the OpenCL ES1.x fixed function pipe. There are all these various stages. I'm not going to go through in detail what they do. And this is kind of the graphics that you can expect. So this was one of the high-selling PC games from the era of fixed function graphics, so around 2005, before the shaders. Now, using shaders changes the pipeline so that there's now, in two parts of the pipeline, the user can write their own code, and that executes in the middle of the pipeline, and there are other like fixed function stages such as rasterization. And then all the fragments are shaded again. That's another user program that runs. And makes this kind of a difference. Of course, there was a couple of year time, but only like a couple. I think this game, the shot is from a game from 2007. The main difference is really that the shaders allow much more expressive graphics. And let's skip this one. So OpenGL ES2.0 is very durable on its API. It has a little bit less kind of hand-holding than the 1.1. There's like really only 4 things that you need to do, and everything else you have to write your code yourself or use somebody else's library. That's not part of the standard though. So there, first is to do the setup. Just initialize the graphic state and the canvases that you're going to draw to and so forth. And then you have this concept of uniforms. They are per object constants. That could be like, for example, if there's a yellow object, that color yellow that's shared by all the triangles in the object, that would be a uniform. Or a rotation matrix for that object might be uniform. Then there are per vertex data attributes. Typical attribute is vertex location, normal vector, texture coordinate. But it's really up to you as a programmer to interpret what it is. It could be mass over vertex, or friction coefficient over vertex, or wrinkliness over vertex if it's part of your face. And you can add that as the character gets older. Anything. And then there are, of course, the shaders. And those are given in as ASCII strings that have to be compiled and linked before you can use them. So the same thing in pictures, maybe a little bit easier. And repetition always is useful. So we have the vertex shader as input. You get the attributes, like the vertex location, normal vector color, and so forth. There are also the vertex uniforms, for example, the transformation matrix that moves the object around. Now, the output is modified vertices. So in this case, we got these 3 vertices, and we have already calculated that this vertex is in this location, it has this color, and so forth. Then comes the next stage of the processing pipeline, like connect these vertices in the triangle and rasterize it. So the rasterization actually tessellates this triangle into fragments that you can think of as pixels. And it also interpolates these values. So by default, it gives like this would be green and this would be red and the middle one would be yellow. And that's kind of the starting input. which your program is then free to modify. And then that it modifies, it gives it a new color, and the color is blended into the frame buffer and put in the frame buffer. So the vertex shader, the first shader, what it can do, it can modify any of the attributes of a vertex. And some examples are things that you could do in the old API, like position, normal vector, texture coordinate, per vertex lighting. But the new things include much more expressive animations, like warping, like jello effects, or and skinning, like human-like or animal objects. Much more advanced lighting models than were possible in the old fixed function pipeline. And then other tricks like doing physics inside of the graphics engine. What you can't do is you cannot, you don't get any information about your neighbors. So it's, you can't ask, you can't clip triangles, you can't tessellate a triangle in smaller triangles, you can't access the color buffer. So in a sense, like one thing comes in, one thing goes out, and that's it. So then there's the fragment shader. So it can and should be like, well, really the main thing is that it calculates new colors per pixel. It can do texture blending, it can apply fog, it can do dependent texture lookups, which means that you, texture coordinates you access from one texture data, but you don't interpret them as colors, you interpret those as coordinates to another texture map. So this allows you very advanced tricks. You can throw the pixel away, you can do font mapping, environment mapping, you can do multiple render targets, which, especially with multipass rendering, is useful. You might use the same geometry to create different kind of outputs, which you then combine in different ways. And you don't have to kind of render the same geometry twice. With fragment shaders, you cannot read from any buffer, including the previous color buffer. That kind of seems a little bit limiting. You also cannot write to any buffer. So you really can only like calculate the new color for this fragment, and then the fixed functionality pipeline does all the remaining things, including blending with the previous colors. Now, why these limitations? This allows the implementation, the hardware implementations, to do various optimizations, such as they can rasterize different elements in parallel. So it can like take all of the fragments from one triangle and parallel rasterize. That makes faster. There's also, when you do blending, you need to go and get the previous color value so that you can do the blending. And memory accesses cost time, there's latency involved. But now, because the hardware kind of knows what's going on and it can like prepare for this, it can hide the latency, which again gives you faster graphics. So a couple of inconveniences that makes your graphics fly, but they are not serious inconveniences. All right, then the previous example was with Java. If you don't like Java, you don't have to use Java. You can use C or C++ even in Android. It's not the preferred way in terms of like Google support. You get the best portability if you stay on the Java side, but you might not get the best performance. So if your application really requires high performance, such as like some action game, or if you do image processing, lots of pixels to be processed, I at least would like to use C or C++ for that. But then if you use specialized APIs that are only available from one particular vendor on the native side, on the C2C side, your application might not run on every other handset. So there's a little bit trade-off. There are various tools. There's GCC that for ARM, but you can run that compiler on your desktop machine and you're not, like I think if you develop for Windows phones, you have to have Windows development environment. If you develop for iPhones, you have to have a Mac. For Android, you can use any computer. If you use native code, you typically need to use Jing, which is Java native interface, which allows you to connect your application side C code to the Java UI. But since Gingerbread, you don't even have to do that. You can, if you want, you can write all your application, including these activity things like that handle the paused and resume state in C++. What that means that then you can use the built-in UI toolkits. You'd have to write your own UI, for example, using OpenGL ES, or you could compile some of the native toolkits, such as Qt. There's a project that runs Qt on Java, so you could use that to make your UI from the C side. So OpenGL ES 2.0 was introduced in Android 2.2, and even on the Java side. But it's for 1.0 you can actually run the OpenGL ES on the emulator. For this, the 2.0 you can run on the emulator. You need a device for testing your code. I'm going to show you how to do OpenGL ES 2.0 on C on Android. This example comes from or the tool to create this example. It's called this app.create.shell. Comes from the SIGGRAPH package. And in this SIGGRAPH package, there are various other examples. There's, for example, this ES2 globe example. But then if you use this app shell to create your own application, it looks like this. So, yeah. So it's a spinning triangle, and there's a little bit user interaction, so you can move it around. So it's a good starting point for then extending your application. The workspace looks like this, and the interesting parts are the main C side C++ file, my app.cpp, and the fragment and vertex shaders, which are in this asset directory, demo.frag, demo.vert. And then there are these various utilities that are also required to run this application. And even though they are provided by NVIDIA, they should run on every Android device. They are just very useful when you do OpenGL ES 2.0 programming. So this is kind of the activity, the main file, main class on the Java side. There are a couple of these things that handle events and do the rendering, but we are not going to touch on the Java side. More of that. We do need, from the C side, to kind of hook our functions somehow to those Java functions that the framework uses. So we want to, these are our C side methods that we connect to the Java methods using Gini. And here are the names on the Java side, and here are the argument types on the Java side. And there's one of the first methods, this is the init. What we have here is, first we have we're going to draw this one triangle. So we put the vertex coordinates of the triangle into here. And then we have the colors here. So the first vertex is red, green and blue. We use a couple of these utility class methods from NVIDIA to initialize shaders, and then to load the program, load and set up and compile the shaders that we have, the demo.vert and demo.frag. Then here we have, here's the demo.vert, so really simple shader for the vertex shader. We first have these per object constants, these uniforms that I described earlier. And the first one of them is rotation, so it's back to, we just have this cosine of the theta, the rotation angle, and sine of the theta that we can use here. And then the translations, also 2D vector, we add the translations here. Then there's the aspect ratio of the screen, we use that here to squeeze the y coordinate accordingly. The next thing that we have is per vertex data. It's those attributes that we covered before. So we have position attribute, it's a 2D coordinate in this case, and color attribute, it's a 4D coordinate. And if we look at positions, they are used here. We rotate this kind of rotation matrix in place, and we assign the output into this geo position, and that's predefined varying. So varyings are the outputs from fragment shader to vertex shader via rasterization. So we give the output position to this vertex. We give the output color to this vertex. In this case, we don't modify the color, we're just passing through. And then what the rasterization does, it interpolates those between the triangles to every fragment. Both positions and colors, and if we add other attributes, it would do. Fragment shader is even simpler. We just copy the input color, and that is going to be the output color that you will see. So you will see the interpolating colors in the triangle. But this kind of just debug code that you could, if you comment this out and put this in, everything is rendered in green. Then there's the rendering callback function. So what's happening here? Okay. So window size, increase the angle of the rotation. Let's clear the color buffer. We need to use the program that was compiled and linked for us. And then we match the attributes by name. So in our shader we had these strings called position attribute and color attribute. We need to match those with our C++ arrays so it knows where to get the data. And the same thing for uniforms. We match based on the names in the shaders the actual data on our C program. And then we tell that, okay, we're done setting up, now draw using that data that I just gave you. There's a couple of more methods. There's the cleaning up after you're done, and input event handling, and this handles the touch event so that you could move the triangle around. That's the whole application. So it's very compact, but does gives a nice complete application. So this is just a picture from OpenVG application. Okay, so I covered OpenCL ES 1.0 with Java, 2.0 with C++. Java is a little bit more portable within Android than C++, but it's not a big difference. However, both of those are restricted to one particular platform, it's Android. If you want to have the same application running on iOS or Windows Phone or Symbian or something, you have to recode. To avoid that, you can try looking into web technologies. those are pretty standardized, so JavaScript is more or less the same everywhere. HTML5, when it's really like available all over the place, it allows much more functionality. Then you can have the same application running everywhere. One thing that you need though is these APIs that are still kind of lacking on the JavaScript side, but they are starting to come out, and one of them is WebGL, which wraps OpenGL ES 2.0 into JavaScript. And it's then available on most main browsers. This screenshot is from my Mac on Chrome. And this picture is my Tegra-based Android phone running Firefox. And it's the same application, same website, same WebGL example. There's a nice website called learningwebgl.com that has kind of stepwise instructions how to get started on WebGL programming. And I think this is what I'm going to cover is example 1. They have example 0 that was loaded too basic, so I'll cover the example 1 if they have any more. The output of the example looks like this. It renders a white triangle and white square. So it's all in one file, or well, 2 files, but it's a regular HTML file more or less. So you have the kind of starting thing, so HTML, and then what you have here is body unload, which means that as this web page is loaded, it's going to call this function that's defined here. I'll show you in a second. And then it also creates a canvas that's 500 by 500 size square canvas. And then there's this script part that has our JavaScript code. And then here we have other things that I'll show you later. But one of the things here is this WebGL start, this function that we call. And then we want to get the handle to the canvas that we created here. We gave it by its name. This is the name and its matches. There are 3 functions that we call Geo Initiators and init buffers. Those don't exist. We have to define them ourselves. They will be in this part of the file. And then after we have initialized, we clear the color to black and then draw the scene with this draw scene that will actually do the drawing. So one of those functions that were a little bit higher than the WebGL init was this initGL. It takes this canvas as input. From the canvas we can get the OpenGL context or the WebGL context, which we store into this variable, a global variable, and we just store the width and height, a little bit error checking and exit. Then here are like a couple of, we have the vertex shader and fragment shader. So the vertex shader it uses 2 uniforms, 2 matrices. We just have our own model view matrix and our own projection matrix. And then it takes the input, this vertex position, and then outputs the output vertex position. And then the fragment shader is really simple. It just shows white pixel. This is one of the utility functions in the same file. We named it getShader. And what it does here, it actually pass this ID, which is kind of the name of the shader, and with that name we fetch it, and then we figure out which type it is, and then we either create the shader that's fragment of vertex shader, then we go and get the content, like the string, and pass that to the shader source, then we do the compile shader, and then we have a compile shader. So this is something, this yellows means that they are the GL code. That you would have needed to do in the C++ example that I showed earlier, except that this NVIDIA's utility library did that work for you already. a little bit error checking, exit. Then we have these initiators, which first creates a program, gets and compiles the vertex shader, gets and compiles the fragment shader, and then links those shaders into this program. Let's check that it's okay, and then use the program. And now we need to attach the attributes, so the vertex data to the strings in the shaders, and the same for uniform split matrices. This init buffers initializes the vertex buffers. So here are the vertex data for a triangle, and we put them, those vertices into this array, and do the same thing for the square. And then this is the second file that's used. So as I discussed earlier, there's really no support for matrix mathematics in the OpenGL ES 2.0 itself. Same goes with WebGL. But it's handy to have, and there's this, it's a really short file like this, and it's going to be in the same directory, and it's included, and that has just a little bit JavaScript code that makes the matrix multiplies easier. And this is how we use them. The blue lines use this mini matrix library. The yellow lines are OpenGL. So this is the rendering called draw scene. So set the viewport, clear the screen. Let's create the 4x4 matrix using this utility program, and set up the perspective matrix, perspective transformation matrix, and let's assign it to the correct uniform. And then the model view matrix, let's assign it to the correct uniform. And then let's put the triangle data into the correct, and let's draw the triangle, move the square, and let's draw the square. And that's it. There's the output. So this completes the graphics part. So but then if we talk about visual input and output, then graphics is the output part. Input part is at least almost equally important, if not even more. And that you can do with camera, among other things. So you can use camera, for example, to capture texture maps to make your graphics more fancy, or you can use cameras to control your program. You could, for example, track your hand or track your face, or and then do something. This image shows a SIGGRAPH DevU platform. It has 3 cameras. There's 2 cameras on the back side. It's a stereo camera, 1 camera on the front side. And it supports these 2 APIs that I'm going to cover. OpenCV for computer vision image processing, and FCAM for camera control. This is kind of really real established API. This is a little bit more of a kind of research project, but it's pretty neat. So OpenCV. OpenCV is Open Computer Vision Library. It was originally created by Intel. Then it was abandoned by Intel, and then it was picked up by other companies such as Willow Garage and INSEAD. And now NVIDIA is supporting it, and some other companies are supporting it. Google is supporting it. It's a de facto standard for computer vision. And it's available on all desktop platforms, and now it's starting to be available on most mobile platforms. So it's definitely available for Android and iOS version. I think beta is out already. So with computer vision, you can create new nifty gesture interfaces. You can do augmented reality games. You can do translations on the fly. You can recognize images and fetch data based on the images. Here's some of the functionality, kind of shown in pictures, what OpenCV can do for you. So there's lots of general image processing stuff, transformations, and there's 3D vision support, there's tracking, there's depth maps, there's machine learning, and linear algebra. It's available for Android, as I said. These are the main companies kind of that Willow Garage and ITSEs are the current home of OpenCV. Willow Garage is a robotics vision company in Menlo Park in Silicon Valley. It's most kind of research company. ITSEs is, you could say that it's kind of spin-off from Intel. They had a team in Russia. One of the teams working on OpenCV was in Russia, and when they kind of reduced their investment in OpenCV, these guys started their own company, and they were on OpenCV. And I don't have to write this down, but ITSEs hosts the Android version of OpenCV. This Android version has a couple of nice example applications of using OpenCV. I'm not going to go through the code, no time for that, but I'll just show the example number 1. Let's take an image and show it. Very compact example, runs nicely on the phone. The second example adds image processing to it, so it has now image processing in real time. So in this case, it's doing edge detection from the camera image view. If you want to use OpenCV on Android, you can choose whether you want to use it via Java or native. Both are available.
So the native is really faster? The demo you showed us.
Yeah, so it really depends like how much time you spend on the Java side, because the library itself is the same. There's a little bit overhead when you have to go. It says mostly the function call overhead when you go from Java to native side, so yeah, it's a little bit slower, but it shouldn't be much slower. Because the heavy lifting, the implementation itself is in C and C++. As far as, like these examples showed, OpenCV makes capturing the image easy. But both the camera API, the built-in Android camera API, and also the OpenCV version that allows you to grab camera image, they are very limited. Basically, everything's automated, like grab an image and you get whatever you get.
Sorry, the image they grab, does it kind of push it through the OpenGL PS? Or
No, it's not via OpenGL. OpenGL is just for rendering, so Android has its own native APIs for camera control. But like all the mobile devices, the control is fairly limited. Like if you would like to set precisely the focal length of the camera, or the exposure time, or the white balance settings or something, they may or may not be available. If you do some tasks such as computational photography, like if you would like to write your own HDR, high dynamic range imaging application, that would require that. Let's take a few images, hopefully really quickly, because I don't want to have lots of handshake, or I don't want to give you time to shake your head between the images. And I want to take the images with different parameters, different exposures, the exposure duration. I get the dark image, light image, and the medium image, and then I combine them. That's not very feasible with the basic given APIs. Or if you want to do a computer vision application where you try to recognize the register plate of a car, you're interested only about the register plate. You don't care about the sky in the background. But if you use automated camera control, like it tries to give kind of you the average good image, and it doesn't optimize it for the register plate. So you might want to have more control than what the system gives you. And that is the reason for this FCAM architecture and FCAM API project, which is available on this Tegra board. It's also available on Nokia N900 Linux-based smartphone.
So what you're saying, video for Linux interface is not sufficient to control the camera?
Video for Linux is pretty good, but it's not very easy to use. It was not designed for fast state changes. It was designed, I think it originally was designed like really fairly general purpose input mechanisms on Linux, and then definitely the main use cases are that you either take one still image every now and then, or you take video continuously, but it was not designed for this that really quickly changed the state in a deterministic fashion. So the first version of FCAM on this N900 actually used video for Linux as a building block quite a bit, but it also had to go underneath that to really implement it. And in a nutshell, what FCAM is, it tries to make this camera system that's usually not visible to the programmer at all. So this is the image sensor, this is the imaging processor, and other related devices. So make all this controllable and available for the programmer in an easy to use fashion. And it also changes kind of way of thinking of camera. So most camera APIs, such as we hear for Linux, they think of the camera as something that has a global state. And that's not true, ever. The camera is a pipeline. There's like, when you're taking current image, then at the same time you're reading out the previous image and you're setting up the next image. And then there's the processing pipeline that comes after the sensor, and there might be one image on the beginning part and one image on the end part of the pipeline. Now if you go and just change the state willy-nilly, like you think you made an atomic change, well, you might affect, like part of the change affects different images differently. You don't even know which ones were affected. So instead, FCAM changes the thing so that there is no state for the system. The state travels with the request. So we request an image, we call it shot. And the state is associated with one of the requests. And then the image goes here, the state goes with it, and then we might have the next image with a different state. And that state travels with it through the pipeline. And this allows, this makes the distinction that now we can take the images faster. We don't, with the kind of previous model, to get the deterministic behavior, you would have to, let's set the state, take an image, wait until the image is passed through all the way, reset, set the new state, take a new image. So you can do it, but it's going to be much slower. And like for example, the HDR example, many of these examples, so there's the HDR, so in this case, like 5 different input images were taken, and they are combined into one output image. This is 2 input images, so this indoors, low light light situation. So this is short enough exposure time so it's not blurry, but it's very noisy and the colors are bad. Here the colors are good, but handheld, the shape, blurry. Take 2 bats and combine the better parts into one group. This like Rank camera version 2.0 from Stanford has two flashes attached. One of them strobes, goes on and off, and that leaves the trail of the cards. And the other one then goes off towards the end, and that freezes the motion. And this is all in focus imaging. So there's 3 images focused, this one in the foreground, in the middle ground, in the background. And then the output image kind of picks up the sharpest pixel from each other inputs, and then now you get everything in focus. Well, these two are still lives. So if you're on a tripod, it doesn't much matter how long it takes. This is more or less still alive, but I'm there. I don't want to stay like this forever. And this is definitely not still live. So if you want to get something where there are people, where they're moving objects, speed is of essence. FCAM is an open source project that's available at the FCAM.garage. So anybody's, it's free to implement it on their system. So I said it's available now on Nokia and Space Phone and NVIDIA Tegra development platform. And one experimental camera at Stanford University. Any questions? On desktop OpenGL, yes. But not on mobile OpenGL, not on OpenGL ES.
So it's not in ES.
Oh, the question was about geometry shader. So where was this geometry shader? Where did I hide it? Well, it's yeah. I guess the Khronos working group hasn't thought that particular functionality, the trade-off or the added complexity to the hardware and the added benefits for the programmer are not good enough to add it to the mobile standard yet. So if you add this, every time you add complexity to the API, that means that the hardware implementations have to be more complex, so there's cost, both of the engineering time and silicon cost, but even more importantly, possibly, is that the device will use more power. Power is key in mobile battery power devices. But yeah, on desktop OpenGL, the geometry shaders are there. So on desktop OpenGL, the functionality is every bit as expressive as Vertex.
So the OpenCV part you mentioned, it will be done on the CPU side?
Yeah, well, yes and no. Originally it was on the CPU side, which you can imagine if it originates from Intel. We have
but they do have the multimedia, like SIMD.
Yeah. And Intel has, adding optimizations also using the SIMD instructions. NVIDIA has, for the desktop side, accelerated many of the OpenCV functionalities using CUDA. So if you have an NVIDIA card and running CUDA, then your OpenCV will likely run quite a bit faster. On Tegra's side, NVIDIA is also working on optimizing OpenCV for Tegra. So, like Tegra 3 has 4 ARM cores, and all of those ARM processors have a companion processor called Neon, which has kind of same kind of instruction set. So we optimize OpenCV to use multi-threading, to use the 4 cores, and to use Neon instruction set. And it has, Tegra 3 has also a pretty powerful GPU, which doesn't have CUDA, but it has OpenGL ES 2.0, which can also be used for image processing. It's kind of the old school GPU. So some OpenCV functionalities may then be also accelerated using GPU.
The OpenCL, what we done the OpenCL. Usually it was a news announcement
Well,
this morning.
on those platforms where OpenCL is available, yes. OpenCL is a good candidate for accelerating OpenCV.
So the edge detection of what kind of things you can do in real time using your camera phone right now?
We have some demos, OpenCV demos. It's like real-time face tracking. There is this augmented reality demo that basically like follows a marker and then draws a 3D element, like 3D object on top of that. What else? I mean, some of those examples that I showed, for example, the HDR sequence that was done on Tegra. Several.
So, media is like for the game part, is it support more on DirectX or?
We support both.
Okay, so then if Microsoft.
Well, on desktop DirectX, well, we sell hardware. We sell hardware to whoever wants to buy, and it's their choice which operating system they want to put on and which APIs. And we are happy to support any of those APIs.
Okay, so
on desktop, we definitely support both DirectX and OpenGL. On mobile, we have OpenGL ES, and we can support also other APIs if the hardware.
So which means Microsoft wants you, like your company, Multimedia, to support their DirectX on their own 7-year
I think so. At least DirectX 9, I think we should be able to handle. Okay, thank you.